Thank you, everybody, for attending this webinar today. I guess more people will be joining in the next minutes. I see, yeah, some people are joining just now. So these initial minutes, well, we are going to take advantage just to well to show you the agenda. So yeah, okay, thank you. So this first 10 minutes or even less than 10 will be used for, well, giving you some general information about the AOTI Agriculture Working Group for those of you that are not familiar with our activities. And well, the next part of the webinar is indeed devoted to the paper that we released publicly last week about biodiversity and IoT technologies. So on my side, I will do just a very brief introduction about well the motivation for the paper and the political and general context what it fits. And then we will have time for other contributors of the paper to explain more in detail, well, more, let's say, the technical approaches and a couple of interesting use cases where IoT technologies are being applied for biodiversity monitoring. And then we will have also time for maybe questions, discussion with the audience, and I think that's it. So yeah, can we move to yes to the initial presentation? Okay, so the Agriculture Working Group is well one of the I would say oldest working groups in AIoTI. It was established since the very beginning. And currently, as you can see, it's chaired and co-chaired, well, by myself. In my case, I'm the executive director of Gradient. We are an RTO in the northwest of Spain in ICT technologies. And of course, well, agriculture is one of the sectors where we are working together with not only with local companies and colleagues, but also all around Europe. And the co-chair of the working group is Max Schulman, who is well representative from Copa Cogeca. Copa Cogeca is basically the representative in Europe of the farmers and the cooperatives of farmers. And well, our working group, as you can imagine, is about okay how to realize the potential of Internet of Things technologies for supporting agri-food and the forestry value chains in this new well situation that we are living and well, which is very well expressed by the Green Deal policies and as we will see. A bit later. So the scope of the activity in our working group covers well, both policies and standards at the European level, of course, collaborative research and innovation, and we also deal with well, what are the key technological developments and gaps in the fields. So next slide, please, just to give you well, an idea about dimension, activity, more concrete activities. We are currently more than 70 member organizations within, I mean, participating in this working group, which amount to about 100 participants. And well, we have a nice interaction within our working group between not only the technologists, I mean, the providers of the IoT technologies and the researchers, but also the ones on the demand side, which in this case is the representatives of the farmers and the cooperatives, also representatives of agricultural machinery. So we try to integrate both sides of the story in what we do because it's more relevant to do it that way. And in the last years, well, we have covered a number of topics related to IoT, digital technologies in the development of well, agriculture. For instance, last year we organized one webinar similar to this one, dealing with the role of Internet of Things technologies in agroecology. And we participated as well in 2020 we co-organized actually preparatory workshops with the European Commission for the definition of the Common European Agricultural Data Space. We also participated very actively in the consultations also by the European Commission on the reference testing and experimentation facilities for agri-food, of course, in this case. And we have published, well, a number of white papers on, for instance, as well on the monitoring of the new of the new Common Agriculture Policy, data marketplaces, IoT. And one of the activities that we are doing continuously, of course, is well, try to facilitate the creation of consortia for cooperating in collaborative research projects, especially in Horizon Europe. We have actually some successful cooperation case in this regard. And well, that's basically it. Okay, also through our relationship,
Hello.
our hello, through our close relationship with the Smart Networks and Services Joint Undertaking, we are also working for
Yeah, no,
positioning
I was only
agriculture.
ringing because I'm aware you obviously flying out tomorrow. Where are you going to? Whereabouts in the States?
Sorry?
Can others go please unmute?
Oh, thank you, Damir. Okay, and well, just to highlight, I mean, our previous activities and to give you examples of the kind of things we are doing, I think this is enough. So just one more slide. Yeah. Okay. So about what we are doing now in 2023, we try to establish every year at the beginning of the year, let's say the main priorities that we will try to push from our working group. And one of the priorities for this 2023 is to increase the visibility, I mean, the public exposure of the results of the activities that we are doing internally, and increasing also the engagement with external stakeholders. I mean, those which are not necessarily members of the working group, but let's say are important stakeholders to be taken into account. This activity, as I mentioned, of promoting the cooperation of working group members for collaborative research projects, of course, this is a continuously ongoing activity. And well, the more, let's say, technical contribution defined as priority for this year is indeed directly related to the biodiversity and environment topics. Because, oh, hi, Alan. Maybe can you mute yourself? Okay, thank you very much. Yes. So basically, the main technical activity that we are promoting this year is related to well, the content of the paper we are going to present today. So yeah, it's almost 10 past 3. So I think yeah, it's now good time to start already with the content of the webinar. So yeah, as I said at the beginning, during the introduction, well, first of all, the main motivation for being here today is that we publicly released in AOTI last week the second version, actually, of this paper, which is the role of IoT and Edge Computing in addressing biodiversity and environmental monitoring. This is a work that we started to put together last year. We released a kind of preliminary version at the end of 2022, and well, we have been doing some refinements and adding more information, and well, working out a bit further the paper during the first part of this year. So this is the paper and the link, which well, you can find in the download section of AIoTI. So next slide, please. Yeah. Okay. So first of all, just to give a very brief introduction about what is the context for this paper, why we are dealing with this topic. Well, the first, I mean, the largest general context. Well, we can find it in the European Green Deal, which, as you probably know, is the flagship European initiative. I mean, the European response to climate change and environmental degradation. So it's an ambitious policy which has a large number of resources and budget associated to it, and many other initiatives which are, let's say, covered under this very big topic. And this, of course, I mean, this European Green Deal comprises many different areas of intervention, ranging from energy, mobility, agriculture, of course. Biodiversity and environment are two of the key areas of under this Green Deal. Indeed, the biodiversity strategy for 2030, this was adopted in 2020 back. Oh, okay. Somebody's requesting put PPT in presentation mode. Maybe, Damir, can you? I guess it's because it's easier to read on the screen. Okay. Anyway, yeah, both. I mean, the European Green Deal. Thank you very much, Damir. Both the European Green Deal and the biodiversity strategy were adopted in 2020. And well, the biodiversity strategy, in general terms, let's say that the objective is to put the European biodiversity on the path to recovery by 2030. Okay, so this strategy sets out, well, a number of objectives, some of them qualitative, others quantitative. Well, these 9 examples, which you can see here in the screen, are, well, just 9 of them. And as you can see, it covers, well, things related to decreasing the use of chemical pesticides, reducing also the use of fertilizers, eliminating chemical pesticides in sensitive areas, reversing the decline in pollinators, well, and also, as you can see, for instance, item number 6 is about is a direct relation between agriculture and biodiversity. Well, objectives related to organic farming and so on. And of course, there is a strong connection between biodiversity and agriculture. I mean, agriculture activity impacts biodiversity in the areas where it's performed, and the opposite. I mean, the biodiversity, of course, impacts very much the success of agricultural activity. So it's not surprising that other of the strategies, the Farm to Fork strategy that was also adopted in 2020 under this Green Deal initiative, shares many objectives with this biodiversity strategy. And we cannot forget either another important policy initiative, which is the Common Agricultural Policy, which was reformulated, let's say, also in the last few years. And different to what happened until now, the Common Agricultural Policy does not only focus on how, let's say, to help the farming activity in terms of producing more food in, let's say, with higher productivity. In this case, there is a very important new element that is being introduced, which is how the farming activity at the same time can be used to protect biodiversity and environment. And this is a very important change in the mindset. So next slide, please. Yeah. Okay. So surrounding this concept of biodiversity in Europe, and as mentioned, I mean, Green Deal is an initiative which is associated to a large amount of funding and many other initiatives. Well, we can find, this is not an exhaustive list, of course, but we can find many strategic European initiatives that have been launched in the last couple of years, including, for instance, the European missions. There are 2 of them which are, let's say, directly related to biodiversity, the one on soil health, and the other one on the restoration of oceans and waters. Probably you heard about also this ambitious European project where also the European Space Agency is participating, which is Destination Earth, which basically aims at building a kind of digital twin of the planet. Observing all the relevant variables related to, for instance, environment, climate, biodiversity, and so on. There are also, in the area of Horizon Europe, there are partnerships like Biodiversa Plus that have been established specifically for taking care of research in biodiversity. This is a co-funded partnership that started very, very recently. And there are also other important policies at the innovation level in Horizon Europe, or in this case in Digital Europe, for instance, like the data spaces strategies, which, as you can see, agriculture and environment are two of the specific verticals considered under this specific strategy for sharing data and making, let's say, profit of the data for the benefit of these sectors. And other initiatives like the establishment of new entities like the Knowledge Center for Biodiversity, which will help in the implementation, the monitoring of the biodiversity strategy all around Europe, and also other, I would say, older initiatives like the Digital Observatory for Protected Areas. I mean, there are many initiatives now at the strategic European level dealing with biodiversity. Of course, as you can imagine, there are also more and more projects within Horizon Europe, which are dealing with biodiversity as well. Actually, the first one listed here, the EU-BON, which is the network on biodiversity observation. This is a project coming from previous framework programs, but it has a continuation in this Europa BON, which started very, very recently. We can find also a project on the building a kind of biodiversity digital twin, which is BioDT. And then, if we take a look closer, we can find also initiatives which are rising at the national level, even regional level. For instance, Arise, this example here is coming from the Netherlands. In Spain, there is also a important project in terms of budget and dimension between several regions about building a system and infrastructure for monitoring biodiversity. And there are many others which of course are not here. You will find more details in the paper. Not everything is covered in the paper, but this is just to give an idea of what's going on. And interestingly, data, of course, here, we are talking about capturing data and analyzing this data and using the data, of course, for taking decision and for identifying trends and so on. So data plays a key role in all biodiversity monitoring initiatives and projects. And interestingly, standardization, even if there are gaps to be covered here, is let's say this is in the game already. The biodiversity community itself some time ago already started to introduce concepts like the essential biodiversity variables, the essential ecosystem services variables, as a way to start standardizing somehow the terms and the variables which are important to take into account for studying biodiversity. And more interestingly, more recently, there are also standardization and technical committees, for instance, in the ISO organization, which are dealing specifically with the concept of biodiversity. On how to exchange in a structured and interoperable manner, and semantically meaningful way information about biodiversity. There are also other technical committees on soil, on water, but everything comes down again to biodiversity. So it's very interesting that we are already going this way. Next slide, please. And well, I'm mostly finishing my introduction. So uh, coming back again to to the motivation for the paper. Okay, this is an agriculture working group. We are working on this topic because, well, as we said, agriculture and biodiversity are two strongly related concepts, and much more recently, well, due to the a strong push by the European Commission of these strategies, Green Deal and biodiversity, and also the new CAP. So. The observation is that, okay, these new environment and agriculture policies are focusing more and more on the preservation of landscapes and biodiversity. And this, in turn, raises the need for measuring and monitoring what's going on with biodiversity. And of course, we need techniques, mechanisms, instruments that are scalable, reliable, and practical. And this is where IoT technologies come into play. Biodiversity is not an easy concept to understand. I mean, biodiversity, well, in a nutshell, is about the measurement of, well, the number, the variety and the variability of the living organisms in the ecosystems. But okay, there is no straightforward translation on how to measure this and using, for instance, IoT technologies. So here we find, of course, as you can imagine, challenges. We find gaps in between what can be done and what is desired to be done. And okay, we have found some real examples also of, well, prototypes, projects that are dealing with this problem, which is good to bring them into, well, to the screen and let you know about them. Next slide, and which is my final one, please. Yeah. So the paper, well, you will find all this information, of course, more detailed in the paper, and the paper finishes with a section discussing what are current gaps and subsequent recommendations about, I mean, on the way to go. Of course, there are other initiatives which are dealing with this problem, but I mean, these recommendations somehow come to complement what is being done now at the European level. So the first recommendation, the first clear one, is that we need to understand exactly, at least the people working on technology, what are the requirements for monitoring biodiversity. I mean, specifically, what should be measured and why it should be measured. In a way that we can bridge this gap between, okay, the biodiversity community and technology community. This is a very important step, and I'm sure Christopher later will elaborate on this need. And then on a more technical level, there is a need for, I mean, after understanding what should we measure, okay, how do we map the important biodiversity features with the physical variables and parameters that we need to measure, directly or indirectly. This is important because this will give the specific requirements for the developers of the technology. And well, the third recommendation is about, I mean, this is dealing with the situation that, of course, I mean, deploying monitoring technologies, of course, it doesn't come for free. And there are also these, I mean, these new requirements which are being imposed in the Common Agricultural Policy to do well in terms of biodiversity. It means that, okay, you need to put some resources in measuring how well you're doing. Okay, so one of the keys to the success in the future is, I mean, to integrate this, let's say, business case aspect in biodiversity monitoring. Otherwise, it will be very difficult, although we will rely completely on the, let's say, the public effort. And it's essential to involve in this initiatives, of course, also the private sector. some of the ongoing initiatives are regarding Green Deal and agriculture. They are directly, let's say, focused at the, I mean, at the data aspects, and an important effort is being done in standardization and interoperability of data. So it's essential from our point of view also to connect from the very beginning these um, initiatives in data with these biodiversity monitoring initiatives and projects in order to not, well, reinvent the wheel. And as we mentioned before, the synergies with the new common agricultural policy, here it's essential to exploit them. In a way that, I mean, this biodiversity monitoring really permeates into the private sector, the farming activity, and in a way that we get a significant, let's say, sources of information and amount of data that can provide uh, well, useful information to take decisions and monitor what is really going on. So this is my introduction so far. So in the next slides, I will give the floor to my colleagues from the Agriculture Working Group, who collaborated, of course, in the elaboration of the paper. So I think we'll go in this order. First of all, Christopher Brewster from TNO will present some, well, general appreciations and the status of, well, monitoring technology and some reflections on okay, some of the gaps that we already mentioned. And then my colleagues Marcin and Alan will present each of them more concrete, practical use cases about okay, putting IoT technologies to work in terms of monitoring of biodiversity. So thank you for for listening so far, and I hope you enjoy the next presentations. So Christopher, floor is yours.
Thank you very much. So let me just talk briefly about the technological advances in biodiversity monitoring. New technologies have changed the way human species are able to monitor other species. For a long time, we've developed, particularly with our obsession with birds and other significantly sort of socially acknowledged animals, ways to track them. So battery technology, GPS, and cellular networks have resulted in wildlife telemetry, which has made extraordinary discoveries, for example, famously tracking birds such as the Arctic tern, which migrate from the Arctic to Antarctica. And related technologies, not exactly the same, are now used in agricultural areas to track cattle in farms. Similarly, but tracking is not the same thing as biodiversity monitoring. So this is an important thing we'll come back to further on. There's a whole variety of methods and tools that can be used directly or indirectly to help with biodiversity monitoring. And that's what I'm just going to quickly give a quick overview here. Next slide, please. So there is the obvious case of in situ monitoring, where you've got an instrument sitting somewhere that doesn't move and that will capture some kind of data. The typical examples are, for example, camera traps for insects. Now very much in combination with automated insect identification. We've used camera traps in agriculture for quite a while to see at what level pests are occurring. And these usually don't use image processing, although obviously more recent versions do. But there are lots of projects now that are using cameras to actually identify specific insects in a specific location. One example is the Arise project in the Netherlands. And this is made possible in part by large imaging data sets, often collected through crowdsourcing. So people, there are various projects around Europe, in the UK, in the Netherlands, and in other countries where citizen scientists are able to send in photographs of whether it's birds, whether it's bees, whether it's butterflies. Those are the favorite ones, particularly birds and butterflies. And so large data sets are collected. Another example of in situ monitoring is acoustic monitoring, for example, for birds and other noisy wildlife. Actually, this originates with whales. It was the first thing that we monitored acoustically. And this has spread to many other different species. But it depends on species having different sounds, and it can only capture specific life stages. So obviously, if, as is the case for some birds, they imitate the sounds of other birds, that doesn't really help you identifying what birds there are. Another interesting example is radar monitoring for birds and bats. So you can continuously scan the heavens, and based on the movement of the animals and the radar shape, you can identify what animals are flying over your scanning horizon. Next slide, please. Now, those are located physically on the Earth, but then remote sensing and Earth observation has been used more and more to do biodiversity monitoring. It's an interesting contrast here. So here we're using satellites, airplanes, and drones, using multispectral and LIDAR scanning for landscape changes. So this is the kind of thing that you can do most easily with this kind of technology, is to monitor large-scale changes over longer periods of time. Typical examples of monitoring of rainforest destruction in tropical regions. And you can look at the health of vegetation as an indirect indicator of the health of biodiversity. And there are some sort of interesting work done on analyzing tree cover and the relationship of tree cover and the quality of tree cover with the quality of the biodiversity. There are more and more attempts to use this kind of technology for more specific species monitoring, but that raises, it's a complex issue to achieve that. Next slide, please. So this is where you get more specific. Using camera traps, as mentioned above, you're able to identify the specific insect. But cameras are static. And this is an important point we'll come back to, as opposed to traditional human transects. The challenge is to collect images to train the recognition algorithms. And as noted previously, there's a great dependence on citizen science for creating these large data sets. And that means that in areas in the world where we don't have so many citizens on the ground engaged, it's more difficult to collect the necessary data sets to actually build these systems. There is an ever greater use of multi-spectral and hyperspectral imaging in combination with species distribution modeling. So you're getting, and you will see this in the next slide, this ever more sophisticated use of integrating multiple aspects of digital technologies, not just the imaging, not just radar, but also with the image processing or the integration with multiple types of data. Next slide, please. So here is another source of data that's of great interest: audio sensors and acoustic monitoring. Extensive use is made of audio sensing. There's a term in the field of passive acoustic monitoring. So you monitor birds, bats, aquatic species. I mentioned whales before, wolves, elephants, frogs, and some insects. Again, you're limited by animals that actually make sounds or that make detectable sounds, because not all animals do that, and not all plants. We generally think of plants as silent, but I'll come back to that. New uses of acoustic monitoring include early warnings. So, for example, tracking the danger of fires, epidemiological research for zoonotic diseases. This is an interesting kind of work to see, well, if we can track the movement of certain species coming closer to human beings, human habitations, then we can spot opportunities for zoonotic diseases to jump. And even soil health. So I'm going to come back to this problem of soil health and the difficulty of monitoring soil health. A major challenge is the interpretation of complex landscapes with multiple species present. So if you are in even an ordinary garden in Northern Europe, but let alone in a tropical jungle, there are so many sounds happening at the same time that our ability to distinguish and pull those apart is presenting a real challenge to our technologies. Next slide, please. So then, as I mentioned, the importance of integrating technologies. Recent research gives examples of multi-sensors or integration of multiple different sensors measuring different parameters. There's a general move towards integration of multiple data, and this is potentially one of the most fruitful avenues because, after all, human beings, when you are in situ in the landscape, you're actually using many different sources of information as a person to understand what's going on, to observe, to listen, and even to smell. And so there are systems now which are using imaging, which are using acoustics, which are even using volatile organic compounds that are in the air, detecting all these things and bringing this together. And here I have made no mention of eDNA because that depends upon laboratory analysis, which is more time consuming. And here our focus is on IoT technologies where you have a continuous access to the data. There is an opportunity here for the development of continuous monitoring, and this is really significant for the agriculture biodiversity interaction, where what we need is not really just snapshots at particular times, but we need a continuous understanding of the development over a particular landscape, over a whole season, over a whole year, over multiple years. And here, this is the area where really more work needs to be done, and we need to turn this into easy-to-use technologies that are more widely available. So let me take the example of soil as an example. There is much work about soil at the moment in smart farming, precision agriculture. We have all kinds of sensors to measure the humidity, the pH value of soil, the electroconductivity, and that sort of thing. But we can't count worms. And yet, if you talk to the agroecological community or the regenerative agriculture community, they will tell you the one measure that you really need to know about in order to understand how rich or how fertile your soil is, you dig a hole and count the number of worms. Well, how can we build technologies using IoT that actually is able to do that? And there are some indications here that we might get there by, for example, using acoustic monitoring, by actually listening to the behavior of the worms in the ground. We might be able to start measuring their liveliness or the quantity there is in a specific area. But for me, it's the fundamental challenge here, or an example of a fundamental challenge that IoT is facing, is how do we count the worms? Next slide, please. So what's missing? Well, I've told you a little bit about what's missing with the worms, but let's talk a little bit about the digital twin conundrum. There are a variety of issues with the technical monitoring of biodiversity. One of the most important issues that people tend to forget about, but is identified by a number of reports, is that funding tends to run out and technology is initially expensive. So you set up a project, you say we're going to monitor all these butterflies in this country or this region, and then after 2, 3, 4, 5 years, the money runs out, and so the data stops being collected. And that's one of the worst things for biodiversity research, is the loss of continuous data. And that's why some of the richest and most important collections of data in biodiversity have been collected by human beings over long periods of time. So we have all these butterfly surveys, bird surveys. There's a collection of people in the UK currently who do bumblebee walks. They every month they go a specific transect across the landscape and count the bumblebees that they see, record them, and send them back to a central repository. So human beings are very important there. So when one introduces technology, if it's not supported over the long term, that creates a problem. And then technology measurements are not necessarily comparable or commensurable with past data. So let's imagine we're talking about the bumblebees. When the data concerns a walk across the landscape of a certain distance, you cannot replace that with just an in situ tool that measures bumblebees in just one location. It is not comparable, it's not equivalent. Another issue is the lack of validation of data. So is the species recognition accurate? How good are the image processing or the radar processing or other? Here you really depend on being able to validate your data measurement technologies. So overall in this area, technologies are good at the extreme scale of biodiversity monitoring, i.e. tracking an individual animal or coarse-grained regional assessment. And a lot more work needs to be done in the middle range of being able to actually monitor a landscape and say, here is the variety and the activity of a whole range of species, whether it's animals, whether it's plants, whether it's fungi, and we haven't even reached the topic of how to use IoT with fungi. There is a need for complementarity with human observation, for continuity of data, for adoption, acceptance, and validity. That is, we need to work with the long-term people who've been committed for decades, if not in some cases centuries, to collect data about biodiversity. And we need to make that data complementary and comparable. And this is important, but we're actually integrating with the community so that the community, the relevant communities actually accept these kind of technologies. But you will say, but we want a digital twin for regional biodiversity. An example is the biodiversity project, which is trying to build a digital twin for biodiversity based on various large-scale data sets from different biodiversity research infrastructures. One of the issues here is that most current data is a snapshot data, even if it is over a long time series. So you're going to collect your bumblebee data or your butterfly data once a month or once a year. The digital twin assumption, at any rate, its original assumption coming from digital twins for manufacturing, is that you have continuous large-scale data feeds. And the CAP monitoring of ecological impacts of agriculture has similar needs. We can't just have one snapshot once a year. Currently, we are far from consistent, we're far from having a consistent, coordinated, and standardized pan-European monitoring of biodiversity. And this needs to be the ambition, both for the biodiversity community itself, but also for the work that the IoT community can offer to contribute towards that. We need far greater collaboration and communication between the biodiversity community and the IoT community, and this has many possibilities. And I hope I've just given you a little bit of a taster of both the opportunities and challenges in this section of the presentation. Thank you very much. Next slide.
Okay, my name is Marcin Płóciennik. I'm from Poznań Supercomputing Networking Center, and I will go more into details for two use cases of monitoring of biodiversity and for integration, examples of integration of several sources of the data and platforms. Basically, while insect pollinators are essential for a healthy nature, bees are, as we know, one of the most economically valuable pollinators of crop monocultures worldwide, and yields of some fruit, seeds, and nut crops basically would decrease by more than 90% without these pollinators. So basically, bees are really critical, important for the environment, economy, as also they ensure pollination for 80% of the crops and white plants growing in Europe. So there are different bee species playing important role in the production profitability of crops like oilseed, sunflower, sherry. And unfortunately, in general, productivity in agriculture sector can be really affected by different factors such as diseases, exposure to chemicals, basically losses in plant diversity, and also some changes in the bees' habits being natural or human factor. And unfortunately, many recent surveys indicate that in general, pollinators worldwide are declining. And this is one of the challenge for the biodiversity, but also in general in economy for food and farm industry. Since they are they contribute at least to 22 billion euro each year to European agriculture. Basically, Europe is also second producers of the ONE. And just to give you an estimation, there's around 7 million of the beehives. But usually there are a large number of beekeepers, but it's a very small number that are the hives that are beehives that are more basically than the guys that have more than 300 of those. So this is really spread around Europe. Next slide, please. So basically, to support the monitoring of well-being of hives, beekeepers can use several dedicated IoT platforms available on the market. Those usually consist basically of the sensor units installed in each hive, which monitors, among others, for example, temperature, weight, position, sound. Then information is transferred via chosen communication protocol, which collects the analyzed data and is presented through different means like mobile applications. So one of these examples is here we present Control B that monitors the apiaries like humidity, acoustic monitor, and then has monitor temperatures, colony development, queen matting, and many others recently. Next slide, please. Previous, okay, yes. So is it not enough? It is not enough to, for preserving well-being of the colonies, as bees can be exposed to different dangerous plant protection products. So what is needed is really close collaboration between farmers and the apiary owners. So basically, currently the communication between beekeepers and farmers is mostly informal and is not monitored, and that leads to many accidental poisoning of bees. And within the Demeter initiative that is basically focusing on the interoperable smart farming IoT, we decided to approach this challenge and allow to make this communication via digital platforms. So one of such platform is presented in previous slide. That was the platform in the apiaries, and here we have another platform that is the Edwin platform, that is the integrated plant protection internet platform, and basically that is kind of the farm management system for Polish farmers, and where basically farmers are having to track all the operations they do in their agriculture work. So the main goal basically of this service was to create and establish a common platform for cooperation and share point information between apiary owners and farmers to enable such exchange. Please next slide. So here the estimation of the number of bee families are needed, for example, to pollinate a given field. There are information how many bee families are needed to provide optimum pollination. By that, we provided the mechanism of the exchange of the data between farm management system and apiary management system. We also provided here the information about spraying treatment alerts. So the apiary owners could or remove their the beehives, or basically they could close it in a given time. So this was achieved through the Matter enablers that allowed for this kind of integration between different kind of the platforms. Okay, next slide. Okay, so maybe my next one would be later on the basically the other use case. So now we move to Alan.
Hello, my name is Alan O'Riordan, and I'm working in the Tyndall National Institute in Cork, in Ireland. So it's been really interesting conversations so far. In my talk, I'm going to present some IoT systems that we've actually just recently developed in an EU project, but call out as to why it's important for biodiversity, even though this specifically wasn't a biodiversity project. But the whole idea of building digital technologies, IoT enabled, to allow real-time continuous monitoring and informed decision-making capacity to stakeholders and regulators and farmers is hugely important. And as Louis said, particularly even since the Green Deal. So if you go to the next slide, please. So the world population hit 8 billion people in November last year and is expected to hit 10 billion by 2050. And that's an awful lot of more people to feed. And the key challenge with this is that we now need to do this more sustainably, obviously, because we've only got the limited land resource or land bank. But we must produce all this food in the context of climate change. So we have increased desertification and lack of productivity from the soil. We have huge competition for land as well, because we're going to have to, those people are going to have to live somewhere. So we're not be building new houses and new homes. And I suppose what's more related to this talk is we have a significant loss of biodiversity in the last 50 or 60 years. And a lot of that biodiversity loss is being driven by the overuse of chemical-based fertilizers, particularly nitrates. And Christopher mentioned earlier on that a very good way of measuring the health of the soil is to actually count the number of earthworms, and he's absolutely right. But it's not just earthworms. We're talking about fungi, we're talking about protozoa, and more importantly, we're talking about the microbiome. So the different microorganisms that live and thrive within the soil has also decreased. So the biodiversity of that has huge impacts then on human health, for example, because we use the soil to grow food that then we eat for nutritional value, and because it's less, we can tend towards illness. So one of the ways of looking at all this sustainability and maintaining biodiversity is obviously to develop IoT technologies that we can deploy out into the field, be they based on chemical sensors or optical sensors or radar or satellite or whatever the technology is. We need to deploy them, and we need to have them all talking to each other. So next slide, please. So one of the kind of better sensors that we can deploy are electrochemical sensors. They're cheap, they're easy to produce, they're very reliable. They begin integrated with electronic systems, analog front ends, connected to the cloud via LoRa or Zigbee or some other communication mechanism, and actually send signals regularly back to a kind of a data support system or a back-end server. But a key challenge with these sensors, you'd imagine, right, so if they're that easy or they're that good, why aren't they all over the place? Why don't we have these chemical sensors everywhere? And the problem is in the technology itself, because you have a lot of electrode drift. You have the reference electrode changes, whether these are electrochemical or ISFETs. So your electrodes drift out, your sensors drift out of calibration within a day if you're not very careful. You need specific modification to make them sensitive to different target analytes. So if you want to measure nitrates, you only want to measure nitrates, and you don't want sulfates or nitrites or any other interfering species giving you false positive or false negative. But most importantly, all of these molecules or all these sensors you need to add chemical reagents generally. This is either in the form of buffers to make sure they're wet and they're stable, or you have to add acids or bases to change the pH. So you're not going to be able to measure you're not going to be able to deploy these sensors in situations where you can't change the chemical environment. So that is a huge limitation to their uptake. So if you go to the next slide, please. So one of the things that we've been doing at Tyndall is trying to develop these chemical sensors for the last number of years now, where we don't actually have to add any chemical reagents at all, that we can do these measurements in situ without having to add anything to it. And of course, the addition of anything to a test solution introduces the possibility of error. So one of the things that we found is that pH is a major problem with measurements. So the pH of the solution you're testing isn't compatible with the requirements for the test. And an example for that would be if you're doing heavy metal analysis in water. Water tends to be between pH 6 and 8, depending on where you are, but you need to be done around pH 3 for heavy metal sensing if you want to do remote sensing. If you bring it back to the lab, that's fine. You can acidify it there. So we found that using electrochemistry, we can actually change the pH of the test environment just around the sensor itself. So we can use an interdigitated electrode array. You see the SEM image there, the false colored image. All the blue wires on the sensor are electrically shorted together, and all the red wires are electrically shorted together, but they're electrically isolated from each other. And what we can do is we can use one of those combs to hydrolyze water. So this is going back to secondary school chemistry, where you run a current across water, you split the water into oxygen and hydrogen. And the interesting thing is when you produce oxygen, if you look at the equations below, you actually produce protons as a side reaction to that. And those protons effectively drop the pH. So using this approach, if your sensors are the red sensors there and you use the blue electrodes to control the pH, you're now in a position where you can measure any chemical reaction that you want to measure, because you can change the pH using just simple electrolysis. And the data on the right shows that you could produce protons, and you see the red circles there. They're the protons diffusing away from the electrode. So to cover the electrode entirely, and that allows measurement. And that's really, really important. And the next slide, please, Louise. Because there's one thing changing the pH, but the other thing is you have to be able to measure it. So you can again use some electrochemical techniques where you just cycle the electrode and you oxidize, say, the gold, then you reduce it back, and that's what these peaks on the left hand side are. And the location of those peaks, the voltage at which those peaks occur, which is the gold oxide reduction peak, is pH sensitive. So by measuring just the location of that peak, you can tell what the pH is. And the two data on the two graphs are on the right there are actually showing the linearity in the position of that peak. For the top one is chemically changed pH using buffers, and the bottom one is electrochemically changed pH. And that's really important, because then that allows us to do measurements in soil, which segues into the next slide. Please, Louise. So here you have an example of a sensor. That's a HDMI pinout, so it's quite small. You have your integrated electrodes on it. You bottom left SEM as you put materials down, which are specific to, say, nitrates in this case. And then you have to package it up, because another challenge that you have with continuous measurement in soil is that it's a very harsh environment where electronics are concerned. So you're putting electronics effectively into a wet environment and leaving it there for 6 months. So you really have to be very careful that you expose only the sensors and that you protect the rest of the electronics, the analog front end to the sensor, to the communications AFEs. So next slide there, please, Louise. So here's an example of what we're doing, which is working, right? Which is the top one is top left graph is the sensor we've developed. It's very sensitive to nitrate, as is shown by the calibration curve there in slide B, or in figure B. But the bottom left one is the problem. Sorry, no, actually, the bottom left one is it's super selective to nitrates, but the bottom right one is the problem there in those four graphs on the left. You can see that it's really sensitive at pH 2. Okay, and your normal soil is between pH 5 and 7.5, again, depending on what part of the world you live. So these sensors are absolutely useless in soil, because you need to add acid. And that's what it shows you down the bottom right. You can see without pH control there, because you get nothing back. You get no signal at all. And this is one of the reasons why we haven't got sensors out in the field and distributed in many places at the moment. It's because we need to add chemical reagents. But in this case, with using the pH control, you can see the emergence of a peak, which is proportionate to the nitrate concentration in the soil, and you can get real-time continuous monitoring back using this approach. So what good is that? So if we go to the next slide then, right? So within this project, we merged the chemical data, the chemical sensors that were buried with optical data. So we created this kind of quadcopter where we put multiple cameras on it. And so we had a range of thermal and spectral and hyperspectral and optical cameras, and we flew the field that we were deploying the sensor in. So if you go to the next slide, please, Louise. And here you have two different images. The one on the back there is the actual Sentinel satellite image of the field, whereas the one kind of superimposed on top of it is the optical image taken from the drone. And of course, the drone is I suppose in much ways better than the Sentinel data because it gives you much better resolution. I think Sentinel gives you 10 meter squared blocks, whereas the drone can go down to 2 meters squared. And using that, you can actually also, if you go to the next slide, you can generate spectral information. So this is providing, for example, how wet and how dry the fields are at any given time. So you're able to see the farmer knows how much water is in the field. Do they need to irrigate? Do they not need to irrigate? But irrigation is really important because not just plants need it. Everything else in the soil also need it as well. So what we did then is, if you move to the next slide, please, we took the soil sensors that we made, we integrated them with moisture sensors, we buried them in a field, as you can see there. It was a field of maize, growing maize, and then we used LoRa technologies to communicate real-time data from the sensors back to the farmhouse. You can see the little LoRa mast on top of the farm on the right-hand side. Next slide, please, Liz. All right. And the farmer, as well as taking our data, went out to into the field every 10 or so days and took soil samples and sent them to the lab. And that's important so you can actually ground truth or benchmark the sensors with real-time laboratory-based data. So you can use the gold standard to tell you how good your samples were. But there was some problems with that. And you can see that in the next slide, please, Louise, that if you look at the data, I don't have a mouse now, so I'm going to try call this. You can see there's two lines there. One has loads of peaks and troughs, and the bottom one is a very kind of flat line, but you can see there's very few data points on it. Right, so that bottom flat line is the laboratory-based assays, right? So they were the dots are the dates when the samples were taken, and the results were put into this back-end server in the project. Now, the squiggly line that's going up and down was the real-time data that was being brought back from the sensors. And at first look at this, you'd say, geez, that's really bad. That's really, really poor. But what you actually realize when you look at it is that the laboratory data completely missed a fertilization step where they actually spread nitrates on the soil, and also missed irrigation when the activity of the soil increased and the bacterial activity increased and more nitrates became available. So that real-time data isn't available to the farmer. So they don't know if they should or shouldn't add another fertilizer. So if we go to the next slide, please, Louise. So where does the IoT come in? So you can take your drone map, right? You can do your hyperspectral imaging of the field, and you can see an example of it on the right-hand side. And you can see those pixels they're 2 meters square, okay? And what you can do then is you can use your soil data, which is in situ. You can read the chemical nature of that, or the chemical concentration of that, and apply it to the color gradients in your map. And based on that color gradient, then you can build a fertilization strategy for the whole field. So if we move on to the next slide there, please, Louise. So the farmer in particular did that in Romania. He loaded his fertilization strategy into his GPS controlled tractor, and the tractor, this was an old tractor, it was 2008, so it didn't have anything fancy. He just basically had a GPS in there, and where it needed areas of less nitrogen, it speeded up the tractor. Where it needed areas of lower nitrogen, it slowed down the tractor, and he was able to populate the whole field with the fertilizer that was needed. And the last slide then are some if you move on, please. The last slide are some feedbacks from the farmer. So they were able to use this IoT system to actually record everything that they did on the farm, Up until now, they were using bits of paper to break down things which they frequently lost. And they could actually watch how the farm was evolving in time by combining different types of sensors, looking at sensor fusion and real-time monitoring. But really, what was really important from the farmer's point of view, and the farming organization is called Spiro there, you can see halfway down the slide, is it enhanced their agronomical activities, okay? And last year, they spread 500 kilograms less over that field than they normally would. Now, that isn't necessarily a huge savings in terms of money. It's depending on the cost of fertilizer at the time, might have been 500-600 euro. But what's really important for them was the environmental hazards, especially nitrous losses, were greatly reduced. And the farmers are working to the Green Deal. They're also working to the Water Framework Directive. They're also working to the Nitrates Directive. And the Nitrates Directive specifies that the polluter pays. So if you're a farmer and you've run off from your field and it goes into the water and it pollutes downstream, you're actually liable for that. So that's a huge risk for farmers. So that's an example of how IoT can help in real time with farmers. But there's many other challenges going forward. So we talked about soil health, but there's animal health, there's plant health, looking at diseases, looking at spread of diseases, looking at spread of pesticides. We need to reduce pesticides by 20% according to the Green Deal. We need to reduce antibiotics to prevent AMR. How do you know if an animal is sick with a virus or a bacterial infection? You need to do lab-based measurements at the moment, in which case it's too late. There's farmer like giving the antibiotics. So there's huge potential in farming for IoT. And all of this is actually related to biodiversity. It's a full wheel, it cycles. It's not just biodiversity is one thing and everything else is separate. They're all interconnected. It's all the microbiome effectively at the end of the day it's affected. And we need to understand the communications between those bacteria, and we need to understand how one event at a soil level will affect animal human health at a later level. Okay, that's me.
Let me just try to find the last slide from Marcin, so that he can present his last case. And then just a second.
It's 27.
I think just a second. Can you see it on the screen?
Yes.
So this one, right?
Yes, exactly.
Okay.
So there is another use case I would like very shortly to present, just 2 slides, so we'll be quick. So this is about another use case and another kind of monitoring that we are doing in Poland. So this is about phenological observation. So basically, this is phenological observation. It's a record of crop of plant describing the different developments stage. So one of such, let's say, events, or could call it seasonal ecological function, is the plant flowering, and this is one of the can be considered as one phenological stage. And this is also a good indicator of the impact of the climate change over the different natural systems, because the shifts of this moment, these phenological stages, basically can be easily detected in and are detected in different taxonomical groups worldwide. So such information about regarding phenology is very useful for data for planning, time execution, and different actions, preventive or protective for the agriculture on different specific stages of the crop development. So basically on the right, you have an example of such systems that we have developed that was composed of several sensors, basically agrometeorological station with different also kind of the sensors in the soil, and where we were collecting those kind of information from there. I'm sorry for the noise, but there is some biodiversity in my home, a lot of the birds in each place, so sorry. Next slide, please. So basically, since already 2011, we have been doing the automated phenological observations. of the different plant species identified in the site of Wielkopolska National Park. And well, the first approaches, as you could see, was with the DSLR cameras. That was, I mean, there was precision needed, and that what was available in this given moment. We basically moved to some other kind of currently very high resolution cameras, and so we built inside of Edwin project basically the infrastructure in Poland. So we built or integrated over 550 agrometeor stations, as you could see on the right, where this is located in whole Poland. But on top of that, we also built currently 20 phenological observation stations, and we plan also in general in future for more. So for automated observation, such phenological observation stations are being placed. There's some noise in the background. Somebody has not muted himself. So basically, such stations are being located in very specific, well-selected place where there are so-called experimental or test fields. So in one place, you have, for example, 20 kind of crops, different kind of plants in a very small fields. Where and with such one installation we can observe a number of those of the stages for the different plants in different periods. So this is usually done in kind of the this is chosen together with agricultural advisory centers or with some institutes that have special fields like that. So in addition, together with our partner from Wielkopolska Advisory Agriculture Center, we also use now those kind of data together with data coming from satellites and drones and from also the sent by farmers through the mobile apps to train AI models for selected diseases recognition in wheat and currently wheat and sugar beets. And the phenological observation are one of the sources. Currently in Poland, we have, I think, over 350 dedicated, we call it signalists, the persons that are doing the manual the observation with given procedure. So we want to enhance this kind of network also with more automatical observation that will basically serve different purposes. And just final word, this is also have long-term planning to preserve this infrastructure. It was said before that usually this is like 2-3 years, there's infrastructure and that's it. So these are long-term planning that are basically a part of governmental kind of services that are provided for farmers from one hand, from other hand could be used also for biodiversity observation. Thank you.
Okay, thank you so much, Marcin, Alan, and Christopher. Okay, so we are still in good timing. So we have plenty of time now for questions from the audience. It could be questions, comments, reflections. So I mean, the microphone is open to you if you want to. I mean, to have any question. For instance, specific to the previous presentations by the speakers, or well, it could be a general question about the topic of the webinar or whatever. So feel free.
We've obviously sent the audience to sleep.
Okay, I see 42 people connected.
Maybe if I
So
can ask a quick question. Um,
yes, I see one raised hand. Yes, please go ahead.
yeah, thank you very much for a very interesting presentations and the paper presentation earlier in today's meeting. One point I wanted to have the presenter's opinion and yourself is what sort of technology? I mean, IoT, we usually think about short range for Bluetooth, Zigbee, Wi-Fi, IEEE standard, but also sometimes 5G standard can play along. What sort of technologies you see for the monitoring and the climate change monitoring activities may actually be more suitable or be the key technology to investigate for these scenarios? Thank you.
You want me to reply, Lewis?
You want to give the first try, Christopher? Yes?
Well, it's widely recognized as a problem with the kind of technologies because rural areas are usually far away from high connectivity. So it's much more likely that you have access to wide area networks like Zigbee or like LoRa. These ones that have very narrow bands, but cover a wide area. So you can't really transmit an image from the middle of a rural area. So this raises the whole issue about edge versus cloud computing, and you need to rethink your balance of where the computing power sits in this context. This may change. I think it's unlikely, but it may change with 6G, in that these kind of rural agricultural demands, and by extension also the environmental and biodiversity demands, will be fed into the design of 6G networks. But currently, if you look at 5G networks, they demand such a high density of transmission towers that it just doesn't occur in rural areas. So you have to solve that somehow else. You have to push the processing to the edge under current scenarios.
Yeah, and if I just join in there, I absolutely agree with Christopher. I don't know if you've ever been in the west coast of Ireland, but you're lucky to get 3G. You're not looking at 4G or 5G for a start. And even when I was on a train in Paris last week, going from Paris to Grenoble, I found connectivity problems in the countryside. So it's definitely going to have to be done at the edge. I'm not sure about LoRa either, Christopher, because the last project we tried to use LoRa and it topographically constrained, it just didn't work at all. And what happened was that the farmer had to go out, literally nearly download it onto his phone from the SDL using Bluetooth, which isn't ideal when you want to do continuous remote monitoring, but you still have to go out and pick up your data once a week. So communications is going to be problematic, and it's going to be power hungry, and that will have to be reduced. The power issues will have to be reduced. Either through reduced power from the electronics, reduced power by doing analysis on the edge, and some sort of definite, I'm a chemist, so I don't know, but so some form of communications that's reliable for very remote areas, even if this is just a drone flying over, picking up the data every now and then, but it has to be worked on.
I should add the biodiversity community and the environmental community is also worried that these technologies placed in the middle of the landscape could deteriorate if they're not monitored. That is, you could have leakages, you could have some kind of pollution environmentally, and they're not convinced that that's been overcome or guaranteed not to occur. So that's also an issue that you have to bear in mind.
And the Green Deal, in light of that, the Green Deal does call out that you have to do no significant harm with your research, right? So the research that you're doing can't cause harm. So that has to be taken into account at the research level as well.
Yeah, if I may add something regarding the connectivity issue, which is currently an issue. Okay, there has always been this kind of universal connectivity solution, which is satellite based. Of course, it has been so far very expensive, so not affordable. I mean, one of the reasons, but probably one of the main reasons for not selecting this kind of connectivity technologies. but things are changing in this regard. For instance, now, I mean, very lately, the first constellations of nanosatellites supporting narrowband communication based on 5G are being launched, and these are intended, indeed, I mean, to give coverage to this kind of rural areas and applications, monitoring applications, which must be performed far away from the cities. So I think very interesting new opportunities are coming in this regard. I mean, and this is actually starting to happen with 5G. Probably with 6G, there will be even better opportunities. But I mean, still, we are at the beginning of the deployment of this kind of connectivity solutions. But this could bring, I mean, this could be a game changer in many aspects, and it could open the way to well, monitoring and sensing applications which nowadays are not, I mean, are basically unfeasible. Just my 2 cents on the question. Anything to add from Marcin? Maybe no.
I think all was said, so I just agree with you.
Okay.
I think, Louise, the main thing will be cost. It has to be cheap. If you look at the cost of Starlink, it's €100 a month.
Yeah. But indeed, I mean, Starlink, I mean, it's let's say a proprietary solution, but now new satellite constellations based on 5G standards are being launched. For instance, a Spanish company very recently launched. I mean, it's still completing the, the setting up of the full constellation, but it's based on narrowband IoT, which is basically under the standard of 5G communications. So of course, I mean, I agree. I mean, the cost is the most determining factor probably in this aspect. But I think, I mean, things are going better. I mean, and will be better in the next years. Now, okay. Thank you, Mona, for your question. Anybody else? We are still in time.
Hi there. Can you hear me?
Yes.
Hi, I'm Natalia from Sensis. We are an IoT innovation center in Scotland. And thank you very much for this presentation. Very fascinating. I didn't fall asleep at all. I wanted to ask for your opinion and at the same time share quite interesting requests we receive with regard to, biodiversity, well, agricultural monitoring. I'm not directly involved, so unfortunately I cannot give you all the details, non-confidential details, but we received a request to monitor the growth of grass. That is, apparently there is some phase in the grass growing that is very nutritious for the animals and then to produce milk and other products. And I was wondering whether you came across kind of this sort of applications for IoT technologies and whether you have some suggestions how to monitor that particular.
Yeah, I can take that. I can take that. I can take that. I can definitely take that.
Yeah.
So there is within Ireland, and Christopher knows what this. Within Ireland, there's a Science Foundation Ireland research centre called Vista Milk, right? And within Vista Milk, there's a whole thematic based on pasture. So there's multiple projects, either both basic and industry funded projects. And some of the stuff they're doing in there, Natalie, is really interesting, right? Because what they're doing, and they were only presenting this last week, so I resonated with your comment that during the growth phase of grass, the initial few weeks is very good because the grass is super sweet and has loads of nutrients. That's really good for the cattle and the animals. So what they're doing is they're using a sward analysis using mobile phones. Right, so they're actually capturing the sward. They're looking at, and they're using image analysis to identify not only the height of the grass, but also the polyculture that's there, whether there are plantains, clovers, etc., existing in the soil. And it's using that approach is how they're monitoring grass, and then they're feeding that into algorithms, right? And they're combining that with the weather. satellite weather data, and they're actually able to build they've built a predictive model on grass growth in the different parts of the country. And it's got to the point now where on the national television service, RTE, which would be equivalent to BBC, every Sunday night, they do a grass prediction forecast for the week for farmers based on this type of imagery. But it's all down to detecting the grass growth, identifying the sward, identifying the other components in there, and then feeding that in with weather data into the model.
But they still can't count the worms.
They can't count the worms, no. Now, remember you saying that to me before, Christopher. Yeah, they can't count the worms. Maybe if we can get them to stand up or something. But they do that on the grass. So it's a real interesting reading of IoT being applied to agronomy, and the tools of the IoT being brought to help farmers in a very it's really important for them, because like they have to figure out their herd size based on how much grass they can produce to feed the animals if it's a pasture-based system like it is here. Yes. But it's really working very well. It's another example of IoT that's being used to
okay, excellent.
And it tracks biodiversity as well, because it tracks different species of plant present in this world.
Fascinating. So I think I make some connections later after the call.
Okay, perfect. I'll introduce you to the people in Chagask who are doing it.
Okay, perfect. Thank you so much.
Yeah.
Thank you.
No more questions?
Since we are 5 minutes to the closure, if there is no any other question or comment, then perhaps we can give just a, let's say, last chance. And if nothing, then I suggest we maybe close the webinar.
Thank you then, everyone. Very, very useful.
So thank you all for participation and being patient. I think we really had very interesting introduction, and even more interesting, I would say, 3 examples. And I would say this really should be considered as a continuous work. This is not one-time thing. We already basically now have released 2 of the paper. So this, let's say, we plan to build on that, add also some, let's say, new findings, expand on topics, new use cases. And of course, if you are interested to work with us on this, you can get back in touch. I think it will be great. And let's maybe take it from there. So thank you all for participation, and have a nice rest of the day.
Yes, thank you, Damir. Thank you, everybody. Just if I may add something, as Damir said, I mean, this work is quite open yet. I mean, nothing close, as you can see. Indeed, in the paper, we open more questions than we provide certainties, of course. Okay, and for sure, we are not able yet to count the worms in the hole. As you can see, we can do something in between. But yeah, one thing I would like to say at the very end is that okay, there are many things going on. There are many European projects dealing with this topic, and as you have seen specific examples of prototypes of promising projects. But what we have found for the moment is very few commercial technologies providing solutions. I mean, let's say not commercial technologies, commercial solutions. I mean, addressing these problems. In the paper, there are 2 or 3 examples, basically on bird detection, classification, the monitoring of bees, pollinators, but not much more than that. So, well, this is well, one thing that we are very much interested in identifying. I mean, as part of the activity to be done, continuing well what is being done in this paper. So, well, if you are aware of technologies, solutions addressing this monitoring problem, we would be very, very happy to know about it. And that's all for my side. Thank you very much again. And okay, I hope to see you very soon.
Okay.
Thank you for hosting this very interesting seminar.
Okay.
Thank you all for participation and have a nice rest of the day. Bye bye.
Okay, thanks.
Nice
Bye.
day.